I'm going to go through like a one-day review of all the calculus that you're going to need for this class. I hope it's not too boring. It seemed like you guys were pretty caught up with this stuff, but I think it can't hurt to have it in your notes for reference. So, okay, here's a calculus review. In one day. So calculus is about two different types of operations on functions. And these are functions of a single independent variable. Well, in the calculus that we're going to do uses a single independent variable, x or t or whatever. So for us, these are going to be functions of one independent variable. And these operations are the derivative and the integral. And these two are related to each other by the fundamental theorem of calculus. And the fundamental theorem of calculus says that these are inverse operations. So they're inverse operations, which means one undoes the other one. Okay, so both of these depend on functional relationships between variables. And so you can't talk about this stuff without being clear about what a function is. That's short for relationship between variables. One variable is independent, and one is dependent. And so, like, for example, if you say f of x is equal to x squared minus 2, then in this case, x is the independent variable, and f is the dependent variable. And obviously it doesn't have to be f and x. It could be, you know, if you have, well, let's say in physics we'll have this a lot where we have a function where the independent variable is t, and the dependent variable is some kind of position quantity. So y is the dependent variable. Okay, and if you have a function like this, once you define a functional relationship like this, you can plot a graph of the dependent variable versus the independent variable. So, for example, if you have x of t is equal to cosine of t, then you say x is a function of t, and when you plotted it, you put x on the vertical axis, t on the horizontal axis, and you'd have something like that. Okay, so in this class, we're primarily going to have two relationships between dependent and independent variables. So two types of functional relationships. The most important one, the most common, is going to be a position variable that depends on time. Okay. So a position variable that's written as a function of time, like, for example, well, I already gave one example, but you could have x of t is equal to 3t squared plus 2t minus 5. You could also have angular relationships where, like, the angle at some time t is equal to 5 sine t, something like that. Less common, but the second most important relationship we're going to have is going to be velocity, some kind of velocity variable written as a function of some kind of position quantity. Written as a function of some kind of position. And that's what we'll see when we do problems using energy. So, like, for example, you might see something that's like 50 times the height of some object is equal to 10 times the speed squared, okay, where this h is a height. This is a speed. And if you wrote that as a function, you'd get something like speed as a function of h is equal to 5h square root positive. Okay. So those are really the two independent variables that we're going to see. Time and then some kind of position quantity. And if the independent variable is a position quantity, then usually the dependent variable is going to be some kind of velocity. once you've decided or established the relationship between the independent and the dependent variable, then you can talk about the derivative. Not until you've defined what's a function of what. So once you've defined what's a function of what, you can define the derivative and the integral. What about things that depend on a lot of variables? You know, like the weather depends on the angle of the sun and the position of the season and the air pressure and all these things. Can you do calculus? Is there such a thing as integrals and derivatives of functions that have a whole bunch of independent variables like that? You have any idea? So what would that be? That's right. So that's multivariable calculus, and that's, I guess, what you would take next semester probably. And that's partial derivatives and partial differential equations, and that stuff gets sort of complicated. But we're not on that stuff yet, and in this class, everything's just going to be a function of a single independent variable. Okay, so for the derivative, I'm going to talk about this as if everything is, so we're talking about a dependent variable f that's a function of x. But this is true no matter what the independent variable is called and what the dependent variable is called. This is all the same. But you'd have something like that. Okay, so df dx is also a function of x, and you can write that as f prime of x. And so this derivative is also a function of x. And df dx gives the slope of the f versus x graph for any x value. By the way, if the independent variable is t, we don't write f prime of t. We write f dot of t. So I'm going to use that notation in addition to, df dt. Okay, and so in the example above, if you plotted out that derivative function, if you plot f prime versus x, so this position versus time, or this f versus time graph starts out with a negative slope, goes to a slope of 0 here, and then starts increasing to a positive slope. And so you get a graph something like that in that case. Okay, so here are the 9 things 9 key facts that you have to know for calculating derivatives. Okay, so first of all, the derivative of a constant is equal to 0. So if this is just a number, derivative is equal to 0. And if you plot out that constant c as a function of x, it's just a horizontal line, and so the slope of it is equal to 0. Second, if you have x2, so d dx of x to the n is equal to nx to the n minus 1. So, like for example, d dx of x to the 5th is equal to 5x to the 4th. And then that also works with negative exponents. So d dx of x to the minus 2 is equal to negative 2x to the minus 3. The third fact, so we're going up to 9. The third one is the derivative with respect to x of natural log x is equal to 1 over x. The fourth one is d dx of sine of x is cosine. And d dx, number 5, d dx of cosine is negative sine. The sixth one is that if you take the derivative of a constant times a function, then that's equal to the constant times the derivative of the function. So for example, if you want to take the derivative of 5x squared, that's equal to 5 times the derivative of x squared, which is 5 times 2 times x. Seventh one, we're only going up to 9, so we're getting there. Derivative of 2 functions added together is the sum of the individual derivatives. So if you want to take the derivative of 3x cubed minus 5x, you just take the derivatives of the individual pieces. So 9x squared minus 5. Okay, the eighth and ninth are the more interesting ones. So 8 is the chain rule. And it says that if you take the derivative of a function of another function, that's equal to the derivative of the outer function with respect to the inner function times the derivative of the inner function with respect to the independent variable. And if you look at those ratios, it looks like the DGs can just cancel out, and you're left with f dx, which looks like it makes sense. So, for example, if you want to take the derivative of sine of x squared, you can think of this like inner function, let's call it z being equal to x squared, and then you have d sine of z dz. That should be dz at the bottom. Times dz dx, which is just cosine of x squared times 2x. Okay, so here's the kind of thing you could be asked. So say that you have position as a function of time, and it follows this function, 5t times sine, I haven't done that one yet, sorry. We'll do that in a second. Okay, so that's the chain rule. And then the last one is the product rule. And the product rule says if you take the derivative of one function times another function, that's equal to the derivative of the first function times the second function plus the derivative plus the first function times the derivative of the second function. So, for example, d dx of x squared times cosine x is equal to the derivative of x squared. So the two functions here are, you can think of this as f of x, this is g of x. So you have 2x times cosine x plus x squared times negative sine x. All right, here's a problem for you to look at for a second, see if you can work through this. So let's say that x of t is equal to 5t sine of t squared minus 10t squared. So first, what's dx dt? And second, what's the slope of x versus t at time equals root pi? Okay. So try to work through that one on paper now. And feel free to talk to each other if something's confusing or whatever. Feel free to ask me questions if you get stuck, but I just want you to get the juices going. So first, to come up with this function dx dt, which, by the way, you would often write x dot, like I was saying before. All right, so we're going to do it in two pieces. The first piece is a function 5t times a function sine of t squared. So we have the derivative of 5t times sine of t squared plus 5t times the derivative of sine t squared. Sine t squared is a function inside a function, so this is cosine of t squared times the derivative of t squared, so 2t. So this whole thing is the derivative of that first term, and then 20t is the second one. So if I simplify this, I get 5 sine t squared plus 10 t squared times cosine of t squared minus 20t. Anybody have any questions about any of those steps? And now if we want to find the slope of the graph at this instant in time, all we do is plug that independent variable value into this new function that we have. So remember, this x dot is a function of time, and you can treat it just like a function. So let's see. We have 5 sine of pi plus 10 pi times cosine of pi minus 20 times root pi. And what do we get for these? This one is 0. And so let's see, cosine of pi is -1, so we get -10 pi minus 20 root pi. Okay? All right, so that's all of Calc 1. It took 40 minutes. Imagine how many classes you could get through if they were all like this. Okay, so now we're going on to the integral. So again, I'm going to use f of x for everything, but it could be, g of t, x of t, z of h, whatever. It's just a functional relationship. So again, I'm going to use f equals f of x. And I'm going to break this up into two pieces. First is the indefinite integral, and this is the one I'm going to spend most of the time on. So this is going to be long. And then the second one's going to be short because we're going to use everything from indefinite integral to define the definite integral. Okay, so first is the indefinite integral. So the integral of f of x dx is equal to g of x where dg dx is equal to f of x. Okay, so it's just, we're defining that indefinite integral as the antiderivative. Okay, it says it's whatever function you need it to be so that when you take the derivative of it, you get back where you started again. So, for example, if you take the integral of x squared plus 2x dx, that's equal to x cubed over 3 plus x squared plus some arbitrary constant c. This can be anything. And we know that this is true whether we know how to calculate this or not. We know that it's true when we take the derivative of this, because d dx of this is x squared plus 2x. So obviously there's going to be a lot of symmetry in the way you calculate the integral, the antiderivative, and the way that you calculate the derivative. So I'm going to go through these 9 steps, and I'm going to do it in a way that they all match up with the 9 that we did for the derivative. So there's sort of a counterpart for each one of those. Okay, so the first one is that if you take the integral of a constant, you get that constant times x plus another constant, an arbitrary constant c. The second is that for any n that's not equal to 1, if you take the integral of x to the n, you get x to the n plus 1 divided by n plus 1 plus this arbitrary constant c. So for example, the integral, so the first one, the integral of x to the fourth dx is equal to x to the fifth over 5 plus c. And you can do it with negative exponents too, as long as anything as long as n isn't equal to 1. As long as n isn't equal to negative 1. So x to the negative third dx is equal to negative 2x to the negative 2 plus c. The third key principle is if n is equal to 1, then x to the minus 1 dx integral is equal to the natural log of the absolute value of x plus c. Now sine and cosine. So number 4 says the integral of the cosine of x dx is equal to the sine of x plus c. Fifth says the integral of the sine of x dx is equal to the negative cosine. Now the sixth and seventh for the derivative were the definition of, showed that the derivative was a linear operator. It said taking the derivative of the sum of two functions was equal to the sum of the two derivatives, right? And taking the derivative of a constant times the function was equal to the constant times the derivative. So derivative is a linear operator. Integral is also a linear operator. So we have those same two requirements. The integral of a times f of x dx is equal to a times the integral of f of x dx. So in other words, the integral of 5t cubed dt is equal to 5 times the integral of t cubed dt. And that's 5 times t to the fourth over 4, which is 1.25 t to the fourth, plus c. Let's see. So what about that c? That's always sort of a weird thing. Like, what about, so that c is an arbitrary constant. If I took the derivative, if I took the integral of t cubed dt, I would get t to the fourth over 4 plus c, right? That should be multiplied by this 5, really, if we're just calculating the integral of t cubed and then multiplying it by the constant. So why don't I have this as 5c here?
It doesn't matter, you just
Yeah, right. So C is random, and so you could think of it as like this. What I did kind of in shorthand is say that I said 5 times t to the 4th over 4 plus C1, and then renamed, so we had t to the 4th over 4 plus 5C1. C1 is arbitrary. Let's just call 5C1 equal to C, and then it all makes sense. Okay, getting close. 7, integral of f of x plus g of x dx is equal to the integral of f dx plus the integral of g dx. So 6 and 7 together say that integral is a linear operator. And so, for example, if you have the integral of 3u cubed minus 2u du, that's equal to 3u to the 4th over 4 minus u squared plus c. And again, you can think of like there's an arbitrary constant that comes from the left one, call that C1, an arbitrary constant that comes from the right one, C2. Add those two together, you get an arbitrary constant that we'll call C. Okay, the 8th principle is sort of the opposite of the chain rule. The chain rule was number 8 for derivatives. So what's the opposite of chain rule? U substitution. So if you have f of u of x dx du dx we can define as, that's the definition of u prime. And then we can solve for dx. So dx is equal to du over u. And then that lets us reformulate this integral as the integral of f of u du over u prime of x. The trick to this is that this only works if u prime of x cancels. So as an example, let's say that we're trying to calculate x times cosine of 2x squared dx. Okay, how about, why don't you guys do this one? Make sure that you can make sense out of this. I'll go through it at the end if you get stuck or whatever, but talk to each other about it. Talk about how awesome this problem is, and ask me questions if you get stuck. So if we set u equal to 2x squared, then du dx is equal to 4x. So dx is equal to du over 4x. And so we can rewrite this integral as x times cosine of u du over 4x. And we get the cancellation we need. We get all the independent variables out of there. And so now we have the integral of cosine. So 1/4 times the integral of cosine u du. This is 1/4 sine of u. And then just substitute back in. So you get 1/4 sine of 2x squared plus c. Any questions about that one? And then the last one is the opposite of the product rule. This is integration by parts, and we're not going to use this in this class, so I'm not even going to talk about it. But that's the one that says the integral of u dv is equal to uv minus v du, and you can derive that directly from the product rule. Okay, so that's it for indefinite integrals. So that's done with indefinite integrals. Now we just have to define this new thing, definite integrals. And so we define the integral from independent variable value a to independent variable value b of f of x dx is equal to the indefinite integral of f of x dx evaluated at b minus the indefinite integral of f of x dx evaluated as a. And this gives the area under the curve from independent variable values a to b. Okay, so as an example, if you had this definite integral, that's 5x squared plus c evaluated at 2 minus 5x squared plus c evaluated at 0. So you get, what's that, 20 plus c minus 0 plus c. The c's cancel, and you get 20. And if you look at a graph of the function versus x, the function is this linear function with a slope of 10. There's 0. There's x equals 2. So we're talking about the area under that curve. And it's a triangle, you know, it's base times height over 2. So that's 2 times 10 over 2. What the? Oh, it should be 20 tall, right. Yes. Math works again. Okay. So you get 20. So it's the same thing. Okay. So the thing to notice there is that when we calculated, when we evaluated this integral at those two values of the independent variable, no matter what those two values are, those constants cancel out, and so you can skip those. The arbitrary constants always cancel out. Okay. So that's it. That's all I'm going to say about calculus. Maybe that was too much already. Okay, so why is this important in physics? The biggest reason calculus is important in physics is that the velocity of a particle is equal to the time derivative of the position of the particle and therefore the position of the particle is the integral of the velocity with respect to time. And the acceleration is the derivative of the velocity, which is equivalent to saying that if you have the acceleration, you can calculate the velocity as the integral of the acceleration. All right. Any questions about any of that? So anyways, now that's in your notes. We don't ever have to talk about it again. But now we're going to go on to something a little more boring. This is the last boring thing. Everything else is going to be super fun. But let's just talk about significant figures for a minute. Okay, so there are, let's see, 5 things I want to say. 6 things. So first, how many significant figures does a number have? The easiest way to calculate that is to put it in scientific notation, and then every figure before the before the 10 is significant. So, like for example, 74.005. So there's like all these rules for, like whether the zeros come before the exponent or after the exponent that can be a little cumbersome if you're just trying to remember those as rules. But if you write that in scientific notation, you get 7.4005 times 10 to the 1. And now every one of these is significant. So 1, 2, 3, 4, 5. Um, 240,000. That's 2.4 times 10 to the 5. And so each of those 2 is significant, so you have 2 significant figures. Okay, so now the operation rules. Anyone remember what you do to the significant figures of the sum or the difference when you add and subtract? The answer has how many significant figures? How do you figure that out?
Has as many as to the last place of the less accurate one?
Yeah, so it's actually not really the significant figures in this case. It's really just the precision. It's how many decimal places it has. And you just truncate the answer to the smallest number of decimal places of your 2 input numbers. You know what I mean? So keep the lowest precision of the inputs. So there's no significant figures really in this. So for example, if you're adding 50 plus 0.001, the lowest precision is the ones place. So you get 50.001, and then the precision that you keep is here, and you don't use those. And if you have like 20.52 minus 10.003, okay, the lowest precision for this one is the hundredths place. you get an answer of 10 point, if you just plug these into your calculator, you get 10.517. We're going to keep this one. We're going to reject this one, but we're going to round it. So you get 10.52. Okay. Multiplying and dividing. Anyone remember how you determined the significant figures for? Yep.
I think it's just use the number of sig figs that the one with the least number of sig figs has.
That's right. So each of your two inputs have a number of sig figs. You keep the whichever one of those is lowest. So if you have 32.1 times 0.53, the lowest number of significant figures is 2. And so the answer is, plug it into the calculator, you get 17.013. And so we're going to keep these two significant figures and not these. So you just get 17. How about raising a number to an integer power? Anyone remember that one, or have you seen that one before? Well, just think of that as multiplying the number by itself a whole bunch of times, and so you just keep whatever number of significant figures you have in the base of that exponent. Okay, so for example, 5.31 to the fourth, 5.31 has 3 significant figures. And so if you plug that into your calculator, you get 795.02. We're going to keep 3 significant figures. So we'll keep these, and we get 795. And actually, this is true for, change this heading. Raise number to an integer power, or what do you call a root that's not a square root? Is there a general name for that? Like a, nth root, let's call it that. You know what I mean, right? Cube root, fourth root. So the same thing there. So if you have the square root of 14.65, has 4 significant figures. plug it into your calculator, you get 3.82753. Keep 4 of them, 1, 2, 3, 4. And this one, we round up. And so 3.828. One thing that I think's, I guess I'm going to try to remember to keep making you practice using the right number of significant figures, just mostly because a lot of you are going to end up taking the AP test, and they'll want you to do that in your calculations on the AP test, I assume. But one thing to keep in mind about significant figures is, like, the idea of significant figures is that it eliminates precision. Like, it doesn't, the hope is that it doesn't indicate precision that you don't actually have in your calculations. But it's a incomplete way to do that. Sometimes it overestimates, sometimes it underestimates. If you really want to be careful about getting your precision right, you need to figure out what your error is, and you need to carry that through your calculations to figure out what your maximum is and what your minimum is. So this is sort of a rule of thumb type thing, but it's not really a scientific, you're not really working with mathematical certainty with it or anything like that. It's just a rule of thumb. Okay. Anybody have any questions about significant figures? Okay. You know what? Let's take a few minutes, get up and run around, go outside, have a snowball fight or something. Let's take 5 minutes, come back, and I'm just going to introduce the next topic before you go, okay? And then we'll start it next time. And so the next thing that we're going to talk about is kinematics of a particle along a line. So we have to define what all those words mean. You probably have the line part down. We probably don't have to define that. Along. You know what along means? Good. Okay, good. So really, I think the two we have to define are kinematics and particle. Make sure that you understand what those are. So kinematics. Kinematics is all the things that that you could determine from watching a videotape of a motion. Okay. These are things that just describe the motion. They don't include any of the causes of the motion. So these are the quantities you could calculate from a video. Okay, so what I mean by that is if you see a, sort of a, say it's actually a black box. You see this little box moving around. You don't know what's inside it or whatever. You just see it moving around, and that's all you can see. You don't know what forces are being applied to it to move it around. You don't know what the thing's mass is. But if there are measurements out there, reference points, you can tell when it gets to each position, and you can tell what its speed is at any instant. Okay, so position, velocity, and acceleration, those are the three kinematic quantities that we're going to deal with, and time. Okay, you could measure the time on a videotape. We're not going to be dealing with force or mass or moment. So no masses or forces. And so what we're going to be talking about is the relationships between the measured time, the position, the velocity, and the acceleration. For some reason, I don't know where these words come from, but it can get sort of confusing because when you do include masses and forces, that area of physics is called kinetics. It's like, why do they have to make them so similar? You know, like it's just unnecessarily confusing. But I don't know. I always think of like, this is the simple one because your ma could do it. But I'm not trying to insult anyone's mom. But that's how I remember it. This is the easy one. Okay. Don't tell Jill I said that. Okay. And then a particle. You might know what the particle assumption is. Anyone know what that is? What are we assuming when we treat something like a particle? Really, all we're assuming is that we're ignoring any length dimensions. So we're not worried about its orientation at all. Assume objects have no length dimensions. Like think about something that has no length dimension. It just exists at a point. It could have mass. It could be 50,000 kilograms, you know, but we're treating it like it just exists at a little point. And if it doesn't extend in any direction, there's no way to make distinctions about what its orientation is. Okay? And so we're assuming objects have no length dimensions, and a consequence of that is we're only worried about how its location changes. We're not worried about orientation. So you can't calculate the orientations. So the first thing we're going to do in this class, the first physics thing we're going to do is just quantify the motion of basically a point, you know, something the size of a point with no size, although it could have mass, as it moves back and forth along a line. Okay? We're going to do that because it'll let us define some quantities that are going to be important later when we go to the more complicated cases of 2D and 3D. Okay, so this is just a starting point. So this section, this topic, is following objects with no size as they move along a line. And that doesn't mean the real object has to have no size. There are a lot of calculations where, you know, even really big things, it's reasonable to treat them as a particle. If you're not worried about the orientation, then you can treat anything like a particle. When you do celestial mechanics of planets in orbit and things, you treat those as particles, even though obviously they're pretty big. But it's because the motion that you're worried about does not involve their changes in orientation. Okay, so here's what we're going to be talking about. This is a ball or something, and imagine it's going this way for a while and then coming back and then going this way. And we're just going to try to figure out a way to quantify that motion. Well, we're not really going to try to figure it out. It's already figured out. I'm going to tell you. That would be weird if I was trying to figure it out and I was up here telling you about it. Really weird. Okay. So at a given instant, so let's, we're going to start by defining position. At the instant, let's say the instant that's shown above, say this is a picture of this ball as it rolls along. What extra stuff do we need to assign a number to that location? To assign a number to that physical location. Basically, we need some kind of reference point and we need some kind of reference direction. Like you could say it's half a mile west of the Quickie Mart, you know, or you could say it's 5 inches from the edge of the table, you know, but you need some kind of reference point and you need some kind of direction. And so before we can put a number to it, we have to define two things. A location corresponding to 0 position, and then if a motion is just along a line, directions are pretty simple, right? You only have 2 choices. And so plus minus sign works well for determining a direction, right? So the second thing we have to do is we have to choose one of those 2 directions to be what we're calling positive, and then the other one is negative, okay? So we also need a direction corresponding to, I don't know, positive direction. So imagine, like, essentially, you're choosing where to set a ruler. And then the object is going to be at the different places on the ruler, and those are going to be the positions, okay? The only difference is that this ruler is infinitely long, and it has marks in the negative direction, too. But that's pretty easy to imagine, you know. So it's an infinitely long ruler. With numbers in the positive and negative directions. Then once you've made those decisions, the position of the object at a given instant is the number it's next to on the ruler. Okay, well, rulers always measure length, and so the units for position always has to be some kind of length quantity. In this class, I'm always going to be using standard international units, SI units. So the SI units for position are meters. You abbreviate that lowercase m. And it always has to be a length unit. So you could define position in inches or feet or miles or whatever. So once you choose this 0 position, and positive direction, you can quantify the changing positions of an object over time. Okay, so, it could go from +1 to -5 to +5 to -20. You can quantify that. What we're trying to get to is we're trying to express the position of this object as a function of time. And right now we haven't talked about how to get time into that measurement. So that's what we're going to start with next time. And so the class tomorrow, normally we're going to do our lab tomorrow, but we haven't gotten quite far enough for the first lab, so I'm just going to keep going with this. But tomorrow we'll have a chance to do some problems and stuff, so you'll at least, you won't have to just sit there and listen as much tomorrow. Yep.
Are we going to be having class in this room or
I think it's a different room. I think it's 1324 over in the Science and Engineering wing at Normandale.
1320?
24.
Oh, 1320.
I think so, yeah. I think so. Okay. Thank you.